Hey, it's me, Brandon. Welcome back to Geology Guy. In the last video, we talked about the lithosphere. In this video, we're going to talk about plate tectonics, specifically the boundaries where two plates interact with each other. Now, there are three main types of plate boundaries, depending on how the plates are interacting right at the boundary. There's convergent, where plates are converging, are moving together. There's divergent, where plates are moving away from each other. They're diverging. And then there's a special kind called transform boundary, which is basically where the plates are sliding past each other. But I'll talk a little bit about why it's called transform and what that really means and why it's special. First, let's talk about convergent plate boundaries. You can think of convergent boundaries as being a collision. It's like a car crash, but in ultra slow-mo. And just like car crashes, not all collisions, not every convergent boundary is the same. For example, a car crash between, say, a Honda Civic and a Toyota Corolla is going to be a lot different than that Honda Civic crashing into a semi-truck. When two smaller cars, or even just two regular-sized cars, crash into each other, they hit and the hoods kind of wrinkle and crunch up. They get shorter this way, but because they get folded and they get wrinkled, they shove parts of the car up. But if a small car runs into a semi-truck, most of that car is going right under the semi-truck. A little bit might get kind of squished up over the top, but most of it's going right under. A similar thing happens at convergent boundaries. Remember, not all crust is the same. Continental crust is usually thicker and less dense, so it sits higher, than oceanic crust, which is denser and thinner, so it sits low and doesn't have as much mass to it. Now, when a continental crust comes against oceanic crust at a convergent boundary, it's more like the car hitting the semi-truck, where the continental crust is the semi-truck and the oceanic crust is the car. The oceanic crust, as it comes against the continental crust, dives into the mantle. In fact, at this point, usually the oceanic crust is dense enough that as it goes into the mantle, it just keeps on going and going and going deeper and deeper into the mantle. In an area like this, we call it subduction. When the plate goes down under another plate, we call it subducting. And so the whole zone on a map where that's happening is called a subduction zone. In fact, there's one right off of our coast. The coast of Oregon, Washington, and even Northern California is a subduction zone, as what is called the Juan de Fuca plate is subducting beneath the North American plate. Now, we'll talk more detail about what actually happens at these subduction zones, but as the oceanic crust is subducting into the mantle beneath the continental crust, some chemical reactions go on to cause part of the mantle to partially melt. So that actually creates a range of volcanoes that are parallel to the subduction zone. So part of a subduction zone is you're actually getting mountains built up from volcanoes erupting right along the subduction zone itself. Now, the Cascade Range is our volcanic range. That's where we have Mount Baker, Mount Rainier, Mount St. Helens, Mount Hood, Mount Adams. All of those mountains, those big, huge snow-capped peaks, those are volcanoes. Some still active, like Mount St. Helens. Some considered active, but dormant. They're sleeping until they're ready to erupt again. And we'll talk more detail about that in a future video. Now, the coast ranges, on the other hand, are not volcanic. They are being produced as the plate is subducting under the North American plate. What's happening is it's just kind of pushing up some of the North American plate. It's similar to this video I'll show you here of a train that was just a little too tall for the clearance of the bridge that it's going under. Take a look at this. Isn't that crazy? You can see the roof just being peeled off. That's similar to what's happening to the Juan de Fuca plate and any other plate that's subducting under a continent, as parts of that plate and material that's being scraped off the plate and scooped up onto the overriding plate. But it's also causing some of the overriding plate to just get squished up and scrunched. Remember, there's an enormous amount of force, an enormous amount of friction here. And so it doesn't just go under smoothly. It scrapes things up and it pushes everything up, and that's what creates the coast range. So when two plates converge on each other, where it's continental crust and continental crust, the two run into each other like two cars. Really, it's more like two semi-trucks. Things get bent and scraped and moved and bumped, but neither one goes under the other. In fact, they kind of build on each other. This is one of the ways we get huge mountain ranges like the Himalaya Mountains. In fact, a long time ago, what is now Africa and what is now eastern United States came together in a big collision that created mountains that were probably as tall as the Himalayas, but stretched for thousands of miles. So this is how we get mountains. Mountains mostly occur at, or very near, convergent plate boundaries. Now that's not the only place that they occur, but if you look around the world, a lot of these mountains are being formed at or near convergent boundaries. However, divergent plate boundaries can also create mountains. Now remember what I said about divergent plate boundaries. That's where the plates are pulling apart from each other. They are diverging. So then wouldn't this create a huge crack in the earth, like in the movie 2012?
I mean, I don't know, honey. I just feel like there's something pulling us apart.
Hang on to the pole! Okay? Don't let go!
Well, kinda. It definitely doesn't happen that dramatically, nor that quickly. But East Africa is actually an area where this is happening. The whole section of Eastern Africa is very slowly, very gradually ripping off of the main continent of Africa. So there actually is a crack going down through Ethiopia, Uganda, Tanzania, Democratic Republic of the Congo, all the way down into Mozambique, if you're familiar with those countries. There is a crack. And the crack really isn't so much of a crack. It's wide enough at human scales that it looks more like a valley. At global scales, it definitely looks like a crack in the earth. But if you were to go stand there in what they call the East Africa Rift Zone, you wouldn't say that this is a gigantic crack in the earth. It's a valley. It's actually what we call a rift valley. As it's forming, the valley actually is dropping and dropping lower and lower. It's creating these faults that produce minor earthquakes. And so on either side, there are these faults, and the middle keeps dropping lower and lower. So at this boundary, the plates have been pulling apart from each other for about the last 25 million years. And as it does so, the crust gets thinner and thinner. And that enables some of the mantle to rise up. As the mantle rises up, part of it can actually partially melt, creating volcanoes that form in that rift valley. In fact, that's what's going on in the Eastern Africa Rift Zone. There's a series of volcanoes that are erupting periodically in the middle of this rift. Now, the lava that erupts out of these volcanoes is chemically the same as oceanic crust. So what happens is this keeps getting thinner and thinner, and more new crust in the form of lava is being erupted out of this area. And so eventually what happens is if it keeps going long enough, then the continental crust gets ripped away from this continental crust. They move apart from each other, and the only thing left in the middle is the lava that forms oceanic crust. And so because of that, and the crust keeps getting thinner and thinner, and so eventually what you're left with is continental crust way over here in one continent, continental crust over here in another continent, with oceanic crust in the middle that's gotten thin and low enough in elevation that it's able to become a new ocean. So because of this, most divergent boundaries that we find on Earth are actually in the oceans, because if they're there long enough, they're going to become an ocean. In fact, these divergent boundaries make gradual mountain ranges with a rift valley in the middle. And because these are in the middle of the ocean, the mid-ocean ridges actually create the longest, if not the tallest, the longest mountain ranges in the world. See, all down the middle of the Atlantic Ocean and across part of the Pacific Ocean and across part of the Indian Ocean, there are these huge divergent boundaries covering large portions of the ocean. Okay, so we've covered two plate boundaries. Convergent boundaries, we've talked about divergent plate boundaries. Now the third one that I mentioned at the beginning of this video are called transform plate boundaries, and that's where the plates are moving past each other, side by side, Most transform plate boundaries are actually small segments where pieces of divergent plate boundaries got split apart from each other. Here's a picture that I took of a piece of road on ground that's becoming a landslide, and so part of the road is actually kind of sliding away somewhat. And you can see that there's a little bit of a miniature divergent plate boundary and a miniature transform plate boundary. Plate tectonics is so cool. It's something we call a unifying theory. See, before we really understood plate tectonics, geologists understood many processes that were going on, but they didn't really understand why some of these processes were happening. They understood about volcanoes, and they understood as well that a lot of volcanoes exist around what's called the Pacific Ring of Fire. A lot of volcanoes existed along the west coast of North and South America, along Alaska, and along the east coast of Asia and in Indonesia. But they didn't really understand why there and not other places. What was different about it? Likewise, some of the biggest earthquakes also happen in the same locations as those volcanoes, but they're not related to the volcanic eruptions. So again, geologists would ask why. They weren't exactly sure. Plate tectonics is a unifying theory because it takes all of these different things and connects them all together. It can explain all of these different processes. Plate tectonics accounts for earthquakes, volcanoes, mountain building, which produces metamorphic rock. Mountains also provide most of the source material for sedimentary rock, so it connects that as well. Plate tectonics is a fascinating topic because of the enormous scales, both in space and in time, at which these processes take place. But it also makes it somewhat difficult to observe. I mean, when was the last time that you went out, stood at a plate boundary and said, "Oh look, I saw it move"? But understanding these processes is really interesting and really fascinating, and once you are able to understand these different processes, you already begin to see the world in a whole new light. Now there's still more about plate tectonics that we're going to talk about in Geology 101, but we're going to save those details for a later lesson. For now, these are the basics that you're going to need to know to be able to continue moving on to the next few subjects that we're going to talk about, like minerals, igneous rocks, sedimentary rocks, metamorphic rocks. Then we will revisit plate tectonics in more detail. Thanks for watching. See you next time.